Assalamualaikum warahmatullahi wabarakatuh. Today we will present our group project titled Insect Classification using SVM with color-based segmentation. This is our group member. Firstly, we have Muhammad Ali Fikri bin Kasim. Next, we have Alif Aikal bin Muhammad Zain. Next is myself, Muhammad Din Hakimi bin Muhammad Yazid. And lastly, we have Muhammad Dia Zulkarnain bin Edi. Insects are the largest and most diverse group of animals on Earth. They play a vital role in our ecosystems, especially as pollinators. By identifying them manually, it's time consuming and require expert knowledge. So, in this project, we aim to automate the classification of insects, specifically bees and butterflies, using traditional image processing and the support vector machine SVM classifier.
For project significance, insects play a critical role in maintaining ecological balance by contributing to pollination, pest control, and food chain. However, manual identification and classification of insect species is time-consuming and requires expert entomological knowledge. This project can be a smart solution that have potential use in agriculture, biodiversity science, and smart technology. This creates a need for an automated, efficient, and accessible classification system. This project is significant as demonstrate a practical and cost-effective approach to classifying and identify two types of insect. There is a bee and butterfly. Using traditional image processing technique that combined with a support vector machine, this is SVM classifier. For the key contribution and significance of the project include that have a automation of insect identification that can be reducing human effort and enabling faster ecological data collection and analysis. And the second is adaptability and scalability, where the current framework can be extended to classify other insect types or biological objects with a minimal adjustment.
Before classification, each image goes through several pre-processing steps. First, we resize it to 256 by 256 pixels. Then we apply color-based segmentation using the HSV color space to isolate the insect. Then we apply a binary mask to the original image. After that, we extract features information from the grayscale version, and finally, the mask image is converted to HSV again for color feature extraction.
Feature extraction. Feature extraction is an important process for our project. For this project, titled Insect Classification using SVM with color-based segmentation, each insect image that has been segmented using MATLAB into a set of numerical values that can be used by the classifier. This is to distinguish between the type of insect we choose, bees and butterfly. This feature describes the shape, fit, texture and color of each image. A total of 13 features have been extracted for each image, which can be divided into three main categories. Feature type. First, we have a feature type shape. The number of features 3, and the shape feature describe the shape of the insect, butterfly and bee through the use of the region props function in MATLAB uh, for area, perimeter, and eccentricity. For the feature type texture, GLCM, number of features are 4. Texture refer to the pattern or roughness of the surface of an object. We use gray level co-occurrence metric, that is GLCM, to extract contrast, correlation, energy, homogeneity. The feature use the gray metric. Use the and grow probes function in MATLAB on a gray image that had it is contrast in H. For the feature type, last one is color. using HSV. Number of features 6. Color is a visual aspect, especially for identifying butterflies. Mass image is converted into HSV, color space for mean, and STD for hue, saturation, and value. It also helps the system distinguish insect not only by the shape and the texture, but also based on their tone and clarity of their colors of on the insect of the image. For the all total for feature type, number of feature is 13 features.
Next, we go to the classification. For this project, we use support vector machine or SVM because this machine helps in classification. Other than that, SVM is good at binary and multi-class classification. So now we go to the implementation process. So at the first, feature input. For each image that has been extracted, such as shape, texture, and color, it will become a feature vector after being combined. And this vector will be the input for the classifier. And the second is label encoding. Each insect, such as bee and butterfly, will be given a numerical label. With this, it will be processed by the classifier. At the third, train test split. The data set will be divided into two, namely training and testing set, using holdout validation. To adjust the model, the training set will be used while to assess the accuracy. And at the fourth, SVM training. A multi-class SVM model will be trained using the function available in MATLAB, and several binary SVM will be used. By default, it is linear, but the kernel function can be changed if necessary. And lastly is prediction and evaluation. Trained data will predict classes of occult test data. In evaluating performance, classification accuracy and confusion metrics will be used. And now we see the image, which is the overview of the SVM classification process. So the first, we extract the insect texture, shape, and color. And next, these features are fed into an SVM classifier, which has been trained on label example, which is bee equal to 1, butterfly equal to 2. And finally, the classifier predict the class of the insect, telling us whether it's a bee or butterfly.
Assalamualaikum warahmatullahi wabarakatuh. And for today, I will elaborate about our evaluation through our process. First of all, my name is Muhammad Daz bin Edi, and this is our uh, processes, which is we are going to access this classifier and to access classify performance and to and send data or test the data. Next, we use the metrics that we use is confusion metrics and also the accuracy. As for the right table, we are using confusion metrics, which we take actual bee photos and actual butterfly photos to be compared the actuals and versus with the predicted labels. So we use two metrics for bee and butterfly classes, where the diagonal are the correct ones, the correct prediction, and the off diagonal is our errors. So to get more accurate data, we are using this formula, the accuracy formula, which is correct prediction be divided by total prediction times by 100. Then we are achieve the data that we want, which is 80% accuracy on the test data. So this is the further technique or the further process that we do, which is key observation, future works, and limitations. So
SVM generalized well using shape, texture, color feature, whereas SV-based segmentation improve feature quality. It is to misclassify often due to wing background overlap and also poor lighting affecting features. For the future work, we use additional metrics, precision recall, F1 score, and apply cross validation for better robustness. Test on real insect images for practical evaluation. So this is the 2 by 2 confusion metric that we the predicted cases that we got, and the limitation is the small database, which is small data set, which is we put 50 images per class, synthetic images to log real world variation. And there we go, we got the pictures where we the pictures that we got throughout our process. Thank you.
Now I will show a live demo. This is the main script. In step 1, we load the bee and butterfly images from the dataset folder. Next, in step 2, we perform pre-processing where each image is resized, segmented, and used to extract shape, texture, and color features. After that, we split the dataset into 70% for training and 30% for testing. In step 4, we train an SVM model using the extracted features above. Then, we evaluate the model using a confusion matrix, which helps visualize prediction and accuracy. Finally, we save the trained model so it can be used by the GUI. Now, let's run the system. After running the main script, three figures will be displayed. The first shows the pre-processing step for B image, and the second shows the pre-processing for a butterfly image, and the third is the confusion matrix that summarizes the model's performance. As you can see here, the model have the accuracy of 80%. Now let's test the model using the insect classifier GUI. For this classifier, we just need to upload an image of either a bee or a butterfly, and then it will tell you what kind of image it is. So let's try a bee. As you can see, it predicted the class as a bee. Now let's try it with a butterfly, and this is also predicted correctly as a butterfly. So that is all for the testing. To conclude, this project achieved 80% accuracy in classifying bees and butterflies using traditional image processing and an SVM classifier. The system includes key steps like color-based segmentation, feature extraction, and a simple GUI for user testing. The results show that classical methods can still perform well on small datasets and offer a foundation for future expansions with more insect types and images. That's all from our group. Thank you for watching.